the screen.
Yes. Can guys see?
Yeah. Yeah.
So yeah, we are supposed to recycle this stream.
Not that one.
This stream. This
Yeah, that the stream. What number stream is that? The top product of the top product of the second stream T202.
Mm-hmm. T202. Yeah.
T202. Yeah. So let's wait, mm, so I think I promised last time that we will look into details on this column. So if you now before we go to the recycle, yeah, can you see there's a small okay.
This one here.
Yeah, can you please click on that? Hey, can you remove this that window? Okay, thank you. So can you make this a little bit bigger? Yeah. Yeah, can you go to the left a little bit? Yeah, that's it.
Right.
That's enough. That's enough. So in here, as you can see, yeah, you can see now it's stage number 1, 14, and 20. Can you see that?
Mm-hmm.
Yeah, stage number 1 is then your reflux is coming in. At stage number 1, 14 is then your feed stage, right? And then 20 is then your bottom stage. So within this column there are 20 stages. So in this case, because we haven't done anything, we don't know yet what the internals are in this column. Yeah. So what we could do is that you could then design the column, the internals of the column, using this tool from HYSYS. So this is a rather new tool. I think they have it already in the last 2 versions. I don't remember. Oh, this is the first versions that they have. This is version
11.
11. In version 10, I think they have it already. So so this will help you in designing the column. Yeah, in our study we use this design book from Kister or from what's it again, Coulson and Richardson, or all of this chemical engineering design book. Uh-huh. But in this case, HYSYS can help you with that. So we just click add new there. Yeah. So in this case, it add new. You can see, if you see, the whole on the left, that column is all in gray. So that means the current one, the CS1 section 1, it starts from stage 1 and then it ends at stage 20. So in all of these stage, they have the same CS1. Yeah, it's one section. And then you can see the internal type is straight. Yeah. So it's a tray. So if you do a drop down, click the drop down, and then you can see different options, either tray or packed. It's up to you. And then use tray first, and then we can see one by one. Yeah. Tray, and then on the right to that, it's a molecular. It's a sieve, bubble cap, and all kinds of stuff which you can just Google. Yeah, in textbook we normally see the sieve and bubble cap, which is then the old styles of typical tray stages. The rest we can just Google them ourselves how it looks like. But then later on, if you see it, you will see it. If you just select on them, you can just see it. We can see the picture later on. Just take, I don't know, see maybe. And then number of passes, yeah, it's just number of passes, so it's one downcomer. And then you can see as well the yeah, the spacing between trays. 0.6 is then typical number, and then the diameter 0.49, which is zero point 0.5 meters. It's also like by default we can you can change this later on. In this case, I think we can see the if you click on the view details, there, next to this diameter, view, click on the view. See, this is then the how it looks like. So you can see on the left, the whole diameter means that's your sieve, because it's a sieve tray. And then and then on the right, it's the side down camera width, because we selected only like one pass. So it goes so it's like if we see it from the top, yeah, of this tray, on the right. So we see that the reflux, the reflux, in one tray, the down camera comes from the right, and then it goes to the left, and then it goes to the next the below tray on this left hand side. So it's something like that, yeah. No, the other way around, then I was wrong. So it's coming from the left, and then goes to the right, and then over the weir, and then it goes down to the second, to the next, tray, and then it's a sieve tray. So if you can see, there is also like a tray type. If you change the tray type to bubble cap, for example, and you can see, hopefully, that one. This is then the bubble cap, so you can see it now. Yeah, so it's much it's a fancy thing now. So maybe you forget this, how this bubble cap looks like. You can either see it in the book, and you can also see it there. So I changed the other one to different type. This one I don't know. So all kinds of stuff, yeah, which you can they have already like a typical sizing and a typical performance of these tray, different types of tray, into the database. So
Okay.
so you have made your choice, yeah. And then valve material, you can just select whatever you want, yeah. It's all up to you. So in here you can play around.
Carbon steel is okay.
Yeah. And then I think can you scroll down if there is anything that says that we can go back or something. We can see also this view hydraulic plots. Yeah, click on that, and then go up. Yeah, okay. And then can you make it bigger? This one is important to see. So you can see, yeah, you can see on that top right hand side, yeah, that big window. So on the y-axis is the vapor mass flow rate, and then the x-axis is then liquid mass flow rate. So it is a kind of like a operating window for both liquid and vapor traffic in the column. So the one that we see now is stage 1. You can see it number, so it's a tray number 1. So you can either see it on the top, this tray 1, or to the bottom of this graph. There's also like 1, 2. Can you see on this? Not on that one. That one is also, you can see. I didn't know that. This is all the map. This is all the map, exactly. That's tray number 10. And this if you click on tray number 11, you will see that as well. So you can click it there. So so if we go back to the to this, yeah, this big graph, what we want the column to operate, that sorry, our operating window, for example, yeah, our liquid and vapor traffic should be within this boundary. Yeah, should be exactly. So should be within that. So we don't want to have a very low vapor mass flow rate. Otherwise, we'll have like a whipping. You can see that 0% whip. So that part is because we don't have any. We don't have a strong vapor to push liquid up, or to pass through the liquid. So hence the liquid will then drop down to the next stage.
Dumping.
So it's whipping, a kind of like a. The column is crying. And then so that means the separation is not going to be yeah, working well in that sense, yeah. And then the other way around, if we increase the vapor mass flow, so it will then shoot out the liquid level on the tray above, right? So it's what we call like a flooding. So all of these froths and whatnot, it can go up to the next stage. So it's also not going to be not what we're going to like. And then the same goes with the liquid mass flow rate. So if we increase the liquid mass flow rate, and it will then overcome this wear load, right? So it will be higher and higher. It will be much higher than the wear load can handle. and if it's if we have like a lower and lower liquid flow rate, and then it will not be able to jump over the weir. So that's basically what these two blue dotted lines mean. And the intention is that to have that you can see that black dot. Can you see that black dot? That one. So we would like to have it actually yeah, as in the middle, as I mean, as closest to the middle as possible, basically. So it's not going to be on the left or on the right. So it's not going to be, we don't want it to be like very close to the boundaries. So you can see, from stage 1 until this stage, I don't know, this can you
Stage
until
10.
stage 13, I think. So in the left, this column, you can see stage 1 until stage 14 is all like a yellow, so they give this warning. And then if stage below that 14 and 20, it's blue, so that means that it's okay. So you can see, 14, 15, 16, and so on and so forth. So this operating point is it's away from these minimum loads, right?
Yeah.
See, it's operating nicely. So if you compare again to this stage number 13, 12, 14, 13, and then the above it, you can see the difference. Yeah, so this operating point is on the lower stages. It goes into the more safer operating conditions, and then if it's at the top, it's not so not so hydraulically it's not that preferable. So what we could do, what can you do, you think? So what makes this problem?
What make
So you compare, just take one picture, this one. So we can see in this in the below, you can see the all stages tab, and also so like stages with warnings. So you can also see that what happens there. And the tab
we have too low liquid mass.
too low liquid, yeah. And then we can then confirm that belief in this in the tab all stages, and then next to it stages with errors and warnings. Oh, it doesn't say. Click detail, click that one. See, stage 4 has a very high pressure drop. We recommend any combination of the following action: increasing the section diameter. See, so it has already like an intelligent how do you call it, help to modify the column. So increasing trace spacing, increasing so you can do there are several scenarios or several options that you can just select from, so that you can then eliminate this warning.
So can we divide it into two sections, one with different
Exactly. So that's
design?
exactly. So we can then go back. Can we scroll down some? Okay, yeah, this one. So we can see stage 14 until stage 20, we can live with this type of tray. But then stage 1 until stage 13, we have to change it. So in this
Yeah.
case, yeah, you can add new. You can add new, and then now you can see I think this one you can exactly change that to 14, for example. And then this one is yeah. So now
We can increase the
you can you can see it first, because now you have already different type of tray. It's a flex TO and then sieve.
okay.
And then the diameter is also like slightly different. So the sieve has 0.5, and then the flex TO is 0.4. And then you can just click also in this view hydraulic plots, and below, yeah. So yeah, yeah.
We have warning. Oh,
So it's the other way around. Now the warning is the other way around. Yeah, even though it was okay last time, but then now with this because we have changed the hydraulic in the top, so it will this the hydraulic in the bottom will get influenced as well, I guess.
Mhm.
So in this case, you can just click at the warning signs. What happens? It also has a high pressure drop. High dry pressure drop means you don't have enough liquid, yeah, basically. Um, so in this case, yeah, you can just play around with what you want, as long as we can eliminate. In this one is a vapor and liquid load.
Uh, can we adjust the
Yeah, you can adjust it.
here? This
Uh-huh.
is adjustable.
Yeah. This is increase, yeah. Uh-huh. And you can also see it from here, yeah. Go to the left, and then below this column there's view hydraulic ports. So you don't have, you just click once.
Oh,
Hmm. Increase the,
we did
yeah, okay, this the other way around, yeah. It's on the top, yeah, exactly.
0.7. That's error.
Error. I think you can just change apa not? Can just change the diameter.
We still got error.
Yeah. Yeah, okay. Or you can just change the type of trace, yeah. It's now this flex TO, and then if you just change it with both sieve, a sieve is okay. Mm-mm. And then
No, no error.
see what happens. View hydraulic plots. All good. It's just that you have now a very strange column, yeah. It's fat in the top and then skinny in the bottom, but it's also like it's only like I don't know, 70 centimeters different. 70
Yeah.
7 centimeters different. So it's okay. I mean, it says 7 centimeters. It doesn't make any difference. But you can increase it the bottom one just to make it like point five, and then it should be okay, I guess. Then you have a nice one,
Yeah.
and then you have a nice column. Now, see.
Also, the Aspen HYSYS would calculate like the minimum diameter requirement.
It gave you in the beginning. It gave you like a default number,
Default.
right?
Okay.
Default number, and then this one you just change it yourself,
Okay.
right?
All right. All good now.
Now everything looks good. Now you can go to your boss saying that, boss, I have designed this column, this number of stages. These are then the internals, right? So you can see. So the internals is then sieve tray, that diameter, that tray spacing, and then you can also show him or her the picture of the trays, right? So
Yeah.
it's nice, yeah. I mean, this is a nice tool, I would say, provided by Aspen, at least for the last two versions. So, is there any question?
No.
No.
Understand. I understand this part.
Yeah, this one is more straightforward. Yeah.
Mm-hmm.
Okay, now we move on to the
Recycling.
so the other students, yeah, because I don't know, I only know you and Shafiq. The other students, do they not have any question?
No, sir.
If no, it's also good. I mean, because again, I need to emphasize this again and again. Yeah, this is more like this is a skill. So if we don't do it ourselves, we're not going to be able to do it. So it's like if we want to learn to swim, we have to jump into the swimming pool. So we will not be able to swim by looking or by watching on how to swim. Okay, so now recycling. So recycling in Aspen HYSYS is different than the recycling in Aspen Plus, and it's also different in recycling in Symmetry or Icon. I don't know about the other process simulation software. I'm not very familiar with them, but at least in these three software that I have been using so far for the last 15-20 years. So how to make recycling is different. So in this HYSYS, they have a call like recycling unit operation. I think you can go open the palette. Yeah, that one recycle. Yeah, yeah. So this recycle, you have to then connect this stream number 13, right? Connect this stream number 13 to this recycle. Oh, 17.
Yeah.
No. This is exactly stream number 13. Because your stream, now you are mixing up the knowledge, yeah? So this is stream number 13, if you see, because this is then the distillate stream coming from the column. So if you see the block,
Okay.
yeah, stream number 17 is then the reflux. You know how much is then your reflux? I mean, do you know how to get that number, stream 17?
From the reflux ratio?
Yeah,
Right.
and then what is then the no, this one you, because you have you are highlighting that small icon. You have to take some what is happening? Column environment, you can click column environment design. Oh yeah, this one. So monitor. Oh, you could also see the performance, maybe condenser boiler or internal. Don't remember. Yeah. Of feed products. This one. That one, reflux flow rate. So you can see that reflux flow rate in the condenser. Yeah, reflux flow rate. That is then your reflux flow rate.
79.5.
Mole. Yeah, or you can also see in the monitor. You can make your own. Yeah, in the connections monitor design, that one. So you know how to view spec. Yeah, you can add spec, and then you would like to see, is there any reflux? That reflux feed ratio spec, reflux, maybe liquid flow. Is there any?
Condenser.
Mass maybe. Okay, yeah. No worry.
This one 79.5.
But it's you put it in mole, yeah? Because we know this number in mole already, but we want to see it in mass, for example. So you can just double click on that and then change it to mass reflux flow. There, 2558. So that's then your reflux flow rate for this particular column. Yeah. So now we just have to connect this. Yeah. Stream 13. Now, this stream is you can name it whatever you want.
Okay.
Yeah. So this part, in this case, I think I have to explain what this means by recycling. Do you know what this means, basically? What this recycling stuff means?
We are recycling our feed.
Yeah, but then how does it do that? I mean, this recycling unit operation, how does it work? Anybody knows? Anybody knows? No? So why do we have to have this recycling unit operation in HYSYS? So how HYSYS does the calculation?
Oh,
If you double click on that unit operation, that recycling, double click, and then you can see parameters. You can, if you click on the numerical, what is in numerical? See, so there is like a two calculation method, nested and simultaneous, and then the acceleration is Weckstein. So what it means basically, there is this Weckstein. You can Google this Weckstein later on, but I will maybe I have to I'll share my screen.
yeah.
Share screen.
Do you want me to send these files to you?
No. I'll just share screen, and then I'll. You see my screen, yeah?
Mm-hmm.
So what we do basically, we have one unit, and then it goes here, and it goes to the other unit, right? And then this part, we want to send it back to the this is your incoming, and then this one you want to send it back to here, basically, right? Yeah. So this then our recycling. So it has this kind of symbol in HYSYS as a recycle. So we calculate, we have done this stream, so I will have to use this. So we do the streams, the 1 2 and then 3 and then 4, and then here you put like 5 for example, or 4 recycle, and then we have done until stream 4, yeah. And then so the stream 4, it will then calculate for us the temperature and then pressure and then flow rates, yeah, basically. And then it will then in this stream 5 is is the recycle, is the stream that's going to be mixed with this guy, stream number 1, to make stream number 2. Remember that I think in the very first sessions of this discussion, HYSYS works in this case like a sequential modular. So it will then calculate from here, and then it has this mixer. It will calculate using the mixer, and then it will go to the and then the stream number 2 will be calculated, and then this unit operation 1, it will be calculated as well, giving stream number 3, and then unit operation 2 will be calculated as well, giving stream number 4, and then R, and then stream number 5 is then given. So we cannot do these mixing calculations if we don't know what stream number 5 is. Can you follow? Yeah, because we have stream number 1, but we don't know what stream number 5 is. So what HYSYS does is that we use like a initial point P and then T prime, P prime, and then F prime, or compositions prime. Yeah, so it will use this as an initial point. So iteration 1, for example, and then 1 plus 5 makes 2, 2 multiplied into u1 makes 3, 3 multiplied within this u2 makes 4, and then in this 4 they have this T, P, and then F. Can you follow?
Yep.
So this guy, what this guy does is then he will then check, is this number T prime equals to T, P prime equals to P, F prime equals to F. So if it's not the same, means they will then calculate the error, yeah? Error ET, EP, EF, and so on and so forth. So they will calculate error. For example, the error is then 10. I don't know, I'm just making some number. So this 10. And then in this recycle, in the Weckstein mode, so they will then just use this number in this Weckstein mode. There's also like a different kind of calculation. So in this Weckstein mode, they will just use this T to the T prime. So this T becomes the new T prime, P becomes the new P prime, F becomes the new F prime. So using this new data, it will then recalculate back this mixing, and then you will get then the new 2. say number 2 and then 3 and then 4 and then you'll get TPF again. So this is then going to be iteration number 2.
So, Doctor, may I ask?
Yeah.
In our case,
Uh-huh.
after we did recycling, there would be high possibility that we would have to redesign our reactor as well as our other, columns.
Yeah, exactly. Very good. Very good. So because when they have this recycling, so this is going to be changing, this guy.
Mm-hmm.
So if this is then going to be changing so if you have this reactor, so the reactor performance may not be as it was before.
Mm-hmm.
Yeah, the same goes with this say for example this distillation column, so this performance will be different as well. Yeah, so if these two performance are not like, if the performance of this and then that are not like robust enough, we will have a difficulty in converging this loop. Yeah, you are getting there. So you will see that later on. Yeah, whether we can then how robust is then the current simulation is. And then especially in this reactor, for example, if this reactor it's a functions of dCA dt, and it's function of k exponent and then minus e rt, right? You can remember this. And then in our case there's also like a partial pressure of methanol, for example.
Yeah.
And then if you have a different stream number 5 will make you a different stream number 2. Yeah, so the partial pressure of methanol will be different as well. So if this then going to be different, temperature is different. Also temperature we keep it constant because we have a heater there. If this is going to be different, that means this whole thing will be different. Number 3 will be different, number 4 will be different, and then if number 4 is different and number 5, they have to adjust, and then so on and so forth. So depending on the robustness of this unit and that unit, so this recycle loop can either be solved faster or lower, or even in some cases also it cannot converge. Yeah, but this whole thing we can see it later on in our simulations. But at least what the message that I would like to convey with you is that how this guy is working, what it does basically. Yeah, so
Okay.
if you I don't know what specialization that you took when your final
Process optimization.
if you put that, that means you learn something about the optimizations. So optimization is then basically minimizing this error. Yeah.
Just doctor,
uh,
say if we have data from a plant,
uh-huh
so we could, make like a mock stream here first, and so all of these
will be quickly
equipment
solved.
will be, as robust as what it is supposed to, as what the plant is
Yeah.
asked. And then when we are recycling, we could just remove the mock stream and recycle the stream. So is it cheating or
No, that's not cheating. That's how we can make the mass balance. Because in the plan, for example, you have the data from this stream, and then you have the data from this stream, but there is no data here. Or maybe you have it here, but you don't know what is in here. I don't know if you have it here. Maybe you have it here. So in the mass balance, the reason for us doing the mass, I don't know if, do you know what the reason is for you doing the mass and energy balance? This is the one of the key important lessons that we have in our chemical engineering school. So what is then the importance of mass balance, mass and energy balance? What is it? Why do we bother even doing that? Have you asked your lecturer why?
uh,
It is to show that the input is equal to output, right?
To show input equals to output, you update, and then and if you okay say that you show it, and then what does it use? So basically, this mass balance is then to help us in understanding what exactly is going on in the plant. So you're right, Shafiq. So this number should be the same as this number. This is stream number 6 maybe. Yeah. So if this is then the plant, so this number, stream number 1, in mass should be the same as stream number 6 in mass. If you see that there are some differences, or maybe stream number 6 is then lower than stream number 1, there must be a leakage somewhere. So if stream number 6 is bigger than stream number 1, that must be some other inputs that we don't know. And then it's also like useful, for example, if you because each of these units, they have their own capacity. And say if you want to make a troubleshooting, or you want to make take, for example, you want to increase the capacity. So since they have the current capacity, the design capacity, and then okay, now currently we are running this with the stream 2 of, I don't know, maybe 10,000 tons an hour. That's too much, yeah, maybe 10 tons an hour. And then you want to say, if I increase it to 11 tons an hour, can this guy cope with that? So that means if this guy can cope with that, you need to calculate stream number 3, right? So that you can then also check if this guy can live with that. Yeah. So to do that, that means you have to calculate stream number 3. You have to really make sure that you get you want what you want with stream number 2. And then if you increase stream number 2 and stream number 3, that means the stream number 5 will change as well, right? And then stream number 6 is also changed as well. And then there are also auxiliary equipment somewhere in the plant that we need to change as well. So we cannot know whether that equipment should be changed or not unless we have the mass balance, and it's also the heat balance, especially if we want to if we are working with heat exchangers or something. So that is also the importance of why we do the mass and energy balance, yeah. To get the to better understand the process, and then to make sure that the equipment is up and running as they intended, yeah, as in the design. If they are not running as per intended, that means there's something wrong. So that something wrong is should trigger us to see and evaluate that specific equipment or that specific process in more detail to see what is happening. And again, to see what is happening, we have to make the mass balance. So to answer your questions, whether if we have this data and we have that data, is this calling cheating? No, it's not called cheating. It's just to help you, because this is then the best you can have. Yeah, you have this, you have that, and then you don't have this number. So that means having this and that. That means you can calculate this number, you can calculate this number, and then you can calculate this number and that number. Yeah, which was not previously there. So because in the plants also, not all streams have flow meters, not all streams have temperature, not all streams have pressure measurements. So in doing this mass balance, we can then at least have a feeling, or a better view on the stream conditions. If the stream, if there is like heat mass leakage, or like a heating leakage, like we are losing heat somewhere. So those kinds of things we can evaluate from the mass balance. I think to better understand that, you can then we'll just later on, maybe we will use an actual case, and then I'll show you how to do so. But at least for this recycle, is there any question? Any question?
No question for me.
No. If no questions, then share again your screen. So let's see if we can quickly converge this uh,
So we remove these two X.
yeah. You have to click on hold first, and then I think it's better that this is coming from. Oh, okay, that stream, yeah.
This was the mock stream
Okay, yeah,
that
yeah,
we
yeah.
used to design. So we include 13 recycle here.
Because the pressure in your stream, no, the pressure in your stream is not as high as the pressure from stream 2, right? So you have to
Yeah.
so that means you can you number one, you can either recycle it to the tank, or you install a pump to so that the pump can then deliver the same the pump can then pressurize that line.
So this is liquid or this is liquid.
How do you know?
Let me see first. This is liquid. Okay,
No, that's not how. That's not the answer. That's not how you get the answer. No. Go back again to that stream recycle. Double click on that. Yeah. Because again, yeah, at the beginning, this is just like your initial points. Remember? So this initial point, you can just put whatever you want. So it just so happened to be that this number is okay.
Okay.
So how do you make sure that this stream should be liquid? It cannot be in a different form, in a different
It
phase.
will be mixing with liquid.
Well, I can also mix gas with liquid, or no?
Well,
Yes or no?
yeah.
Yeah. So what makes you so sure that that stream should be a liquid stream?
I'm not sure.
Not
It can
sure.
be gas.
Any other guess from the audience? So this stream comes from what? Which part of the process?
The condenser.
From the condenser, and then your condenser is a partial condenser, a total condenser. From which part of the condenser that this stream comes from?
Total.
Total condenser. So that's only like one stream coming out of the total condenser, right? So that total condenser and that stream should be in liquid or in gas form.
Should be liquid.
Liquid.
It should be in liquid. So that's the answer. So that stream cannot be in any other phase. It has to be in liquid because it is coming from the liquid part of the condenser. Right? It's a total condenser. So now we have to pressurize it with pump. Then we have to make sure that the pressure is the same as the pressure pressure 2, yeah, pressure of stream 2. Yeah, energy, yeah. And then go to parameters. Or maybe worksheet, I don't know, or worksheet, and then you can just specify the outlet pressure. You can specify the outlet pressure.
155.
I don't know. Yeah, is that so?
Yeah.
Okay.
I don't do this.
Yeah.
Need to active back, right?
Okay. Yeah. Right.
Oh, but
No. Click on hold.
It's okay already.
Yeah. Okay. Close. So so that part is okay. And then that's the thin recycle. You have to send it to that mixer, right?
Yeah. This one here.
Yeah, because you put it on hold.
Can we go active?
Try. So you can see now it's still running. Yeah, you can see the below. It says still running, doing something. At least it's doing something in the column. You can see all of this dark blue. It stops at this T201, right? So that means this T201 is still now doing the calculations. So you can just click this T201 to see what is happening.
Solving.
So solving. Can you make it bigger? Why is this? No, not this big, but
Okay.
Go to monitor, yeah.
Duration given as it.
See, so this unconverged. Why? Because well, your reflux ratio is okay, but then your distillate rate is not okay.
Yeah.
So because now the input is different, yeah, compared to the previous simulations. Your input could be we don't know how much is then DME is being produced. Yeah, so
Can we active DME recovery instead of
yeah, you can do whatever you want, Aisha.
Okay, let's try. Okay, converge.
Easy.
Unconverge.
Unconverge. No, give it. So do you know why it's converge, unconverge? Quick run again.
Unconverge.
Yeah. So it's a 9955. It's the current value is 9955, and you specified it only like 0.99. So yeah, if you want to increase that specified value to current value, you could also do that. Yeah. And see what happens. Fine.
Still unconverge.
Unconverge. See what happens. Close this window. Not converge.
Yeah.
Check that stream number 9, because what you want to separate is in the stream number 9, and it gives you a hint on what's coming exactly. So you have like a 10% of methanol, and so for sure that there should be a methanol in there. So 10% of methanol, how much is that methanol coming? Oh, sorry, this is the DME column, yeah. So it's a 44% of DME. How much is then DME coming basically in flow rates? So 296.1 multiplied by 0.4439, that is then your DME flow rates coming in. So now it's up to you, yeah, whether how much you want to recover.
130. I don't know.
Let's monitor. Yeah, you're sure that's 130?
Just converge.
Unconverge. What is happening?
That's or is it because we cut down the column?
No, it has nothing to do with that. Because you can still you can see you are achieving now the DME purity almost close to 1, and then DME recovery of 0.995. So it's all good.
So
You need only
are we
two.
stuck?
You need only 2 tick. Click run.
But we are the current value is
Yeah, very close.
higher than
I know.
specified.
Well, sometimes I don't know. Yeah, click reset, and then click run. Column fit number 9. This doesn't have any.
Does not have enough information.
It has no.
Let's see.
Double click again. Click run. Column feed stream 9 does not have enough information for the column to run. Yeah, I don't know what happened. Go to monitor, because it has to be, I mean, stream number 9 has enough information, I would say. So
What can we do?
you could do also another thing, yeah. If you now in this case you can then the recycling unit operation is not necessary that you put it there. Yeah, so that recycling unit you could also put it like upstream of stream number 9 and then downstream of that valve 100. So that means you make sure that your column is always being supplied with data. Right, that was the complaint by this HYSYS, right? It says that stream number 9 doesn't have enough data, but in fact it has all the data.
Hmm?
So in that sense, I don't know. So at least to follow HYSYS recommendations, so we will just use this. We will then relocate that recycle unit to stream number 9, so that you have the stream number 9 as the input value. I'm not really
Okay.
sure if you understand everything that I said.
No, I don't.
Uh-uh. So
Okay.
um
What am I supposed to do? Relocate stream number 9 to, as in breaking it.
yeah, you break it stream number 9, break stream number 9, stream number 9, and then the valve in between stream number 9 and valve.
Stream number 9 bar.
Yeah, that one. And then get the information from the steam table or from your plant, the steam table for stream
Uh-huh.
number 9.
Alright.
So you have
And fill it here.
temperature, yeah, temperature, let me see, temperature is stream number 9,
89. Pressure
89,
is
10.4,
10.5.
10.5 maybe. And then the flow rate is, because it's in moles, yeah, you can just go to the moles, go to compositions, because then you can just directly um, yeah, and then change the basis to mole flow rate. Yeah, you can just and then change it to mole flow rate. Then you put the mole. One DME 130.5, methane water is 132.9, methanol is 64.9. Then click OK. There.
Yeah.
See,
Okay, something
immediately.
wrong.
So now that recycle you have to put it upstream of stream number 9, and then you can just directly feed this stream number 13 to replace that pump P100.
P100.
Yeah, so
I'm sorry again.
you can remove that recycle unit and put it upstream of stream number 9. Can you follow? Because now
No.
we are going to recycle stream number 9. We're not currently we are recycling stream number 13, but it doesn't work. So we have
Okay.
to now recycle stream number 9.
So these two here.
No, so that means you have to then yeah, the recycling is then goes to stream number 9, but then stream number 13 is no longer connected to the recycle.
Okay, this one here. This one here.
No, 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 no. Your stream number 13 is, where is the stream number 13?
This one.
Yeah, so it's not going to be connected to the recycle anymore.
Okay.
So that means we have to break that. To the right a little bit.
Okay.
So you send that stream number 13 to your pump directly.
Alright.
Yeah,
Okay.
you can see. So something happens in your heater, which I don't know why.
Right. Something happened to the heater.
Double click. Unknown duty. That is not connected to anything, right? I mean that stream.
No, it's not.
So if you change that 154, delete that 154 and then type it again. 154. Temperature. Delete and type it again.
Unknown duty.
Very strange, yeah? The stream is there. The duty is not there. I don't know.
We input the delta P and the delta T, so I don't think there's be a
Yeah. So this HYSYS is doing any strange stuff that we don't understand.
Sorry.
So if you just put like a dummy duty and see if it works, it will not work. I mean, it's not correct, but just to set it free from any calculation stuck, just put a number.
Any number.
Before. See, error, and then delete that number, and then click active.
Click.
Active. Click active. There.
Okay.
See. Now.
Okay. Now we this.
Yeah, so that means we have to add another stream downstream of that valve.
To recycle.
Send it to the recycle, and then stream number 9 will then be the output from that recycle.
Oh, okay, I see.
Yeah.
Okay.
Can you see now? Wait a minute. Don't be that quick because we don't know what is happening. So stream number 9 is there. So open that stream number 9 recycling, and then number 9 is there. So number 9 is to have the pressure of 1050, and then your number 9 recycling, its pressure coming from the valve, right?
Yes.
So in that valve, can you go to the valve? So in that valve, because you need to make sure that stream number 9 is 10.5. So at least we need to make it like a stable number. So in this parameter, instead of keying in delta P, we should then better key in the outlet pressure.
Oh, okay. So
to make it just to make it more robust, to make the simulation more robust. Because in practice, then you can then have a pressure control here.
Okay.
Yeah. So your temperature is 88.54, and then we want to have it like an 89. Can you follow me?
Yes.
And then the flow rate is almost the same, right? The same flow rate, but then the vapor fraction is different.
Yeah.
Yeah, and then the compositions may also be different. So that is then the one that we are going to minimize via this recycling. So
this is symbol of flow.
Yeah, so it will be changed accordingly. So now try to connect this to the if this is not working, and then we'll have to continue next week. Yeah.
Okay. Not solve everything.
Now your column 202 is now is doing something.
Okay.
Can you open that column 202? What is happening?
I think it's
I mean, the spec. The spec is more important because that's then how we control the monitor. Yeah, this spec.
it's
So you can see, you can see now the methanol purity is not increasing, and then the methanol recovery is also not increasing. So that means we don't know what is happening, at least, but it's now trying to calculate that, because if methanol recovery it's very low, and then the purity is also very low. So both are low, but then it can increase the methanol recovery, uh, as well as increasing the purity by putting more reflux and then more energy to the. And then you can here it's not converge. You can I think you can try to rerun this again.
Should I change the degree of freedom to something else?
Up to you, but I don't think so. At least not for now.
Or just try to rerun?
I will start from that. I don't know what is happening. So in this case, so can you go to the worksheet so that we know what is, because we need to know what is coming in before we are able to separate them. So stream number 12 is coming in, and then you can see then the composition. So it must have like a DME there. You see?
There is.
So you have a DME there, so that prevents the methanol from being pure. So that means the problem that
is with
exactly. So that means we need to make sure that there is no DME coming to the other column.
DME. Let's change this to this.
Run.
Okay, we are 0.99.
This is still running. Now purity is increasing.
Purity is much higher, but the reflux ratio is huge.
Exactly. Because you need to increase the purity. That's what it says. So in this case, I think yeah, I don't see that the purity is going any better. So you can then reduce the specified value later on, yeah, and then the recovery. So that means this recovery, because it doesn't recover methanol to the top. So that means there are methanol in the bottom stream, which we have to remove. So I think we will at least I will stop it here, and then I will let you struggle for next 1 week, and then see what happens. I mean, you can use from now on. I believe that you can utilize all of the knowledge that you have to try to converge this column at least.
Okay, I'll try.
And then just try, and then if it's not, you can then reduce the recovery, or you can increase or change the purity and so on and so forth. Because everything is done based with this first principle thermodynamic and mass balance, so it should be there, not converge. Can you run again? So you can reduce the recovery. So the 97. 0.97. Enter. Enter. And then run.
And converge. Okay.
Then we have another problem. Yeah? Good, very good. So I will leave you to this. Yeah, try to converge this, and then
Alright.
I'll see you next week.
Okay.
Yeah, good.
Alright.
Good effort, yeah, Aisha. Send me this file.
Okay. Alright.
Yeah, thank you. Bye bye.
Bye. Thank you, doctor.
Yeah, send me the file. Yeah.
Okay.
Baca.